Well, the first thing is, welcome to Trinity. It's great to see you. Hi! I've got one friend at the back. So it's great to see you here. My name, just so you know, my name is Sylvia Draper, and as you can tell, I'm a Brit, I'm afraid. I came here, that's me here. I came here 20 years ago because I married a Galwegian, and I have 4 fantastic kids. 2 of them are here today. And I have a few roles, and I have a couple of uniforms. So, first of all, I'm a mum. And then the second thing is that I'm the head of the School of Chemistry. So that means on very special occasions I get to wear this very important looking gown. And that's because I've spent about 8 years studying chemistry, and I got my doctorate in Cambridge, and then I met this Galwegian fella and I ended up over here. Been here ever since. But my other uniform that's not very important at all, is the uniform that you would associate with scientists, and that's this. It's the white coat. And the white coat doesn't make me any different from when I'm wearing my ordinary day clothes and my jeans. It makes me no different. It just makes me safe. It's my uniform. The reason it makes me safe is because you can see me out of the corner of your eye. If I was to run past you, if I was to do something dangerous, then you'd be able to see. So I'm going to put on my white coat today, because I'm going to attempt to do a few dangerous things. So, now, life without chemistry. I wanted to become a journalist, so I did English literature, physics, maths, and chemistry at school. And then I was very confused, and I ended up, in the end, being a chemist. And I've never regretted it. And the reason I became a chemist is because it's changed my view of the world. Now, everything in the world is matter. Matter is simply something that has mass. So you and I are chemicals. And it is, in fact, a chemical reaction that is, at this moment, sending messages through your brain. It's chemicals that are making me able to talk, and it's chemicals in my brain that are translating the visual image, which is you, and allowing me to make sense of it. So what is chemistry? Well, now, just find a slot and move in. So if you're on the edge, if you wouldn't mind, if you slide in, there is a chance that you could be sitting next to a future husband or wife. This has happened to me. This has happened to me 3 times, that I have predicted a future lifelong relationship on the basis of who you sat next to in this lecture. So be careful. If you want to leave a space, I understand. Anyway, life without chemistry, I'm going to keep losing things, but life without chemistry would be very strange, because chemistry has an influence on all of these things. Some of them sound very boring. But things like pharmaceutical industry makes drugs that allow you and I to now live much, much longer. Our life expectancy is increasing year after year after year. And what do chemists do in the process? Well, have what I call a molecular craftsman or craftswoman, somebody who made the chemicals and can change them, and then by trial and error test them out. The pharmaceutical industry would be reliant on things that they could get from nature. And things that you can get from nature are somewhat limited. And still you need a process by which to extract materials from nature. And that also is the job of the chemist. And then over here you can see green chemistry. Now without green chemistry, some of the things that if you like, the footprint of mankind on this globe would be much, much, much more problematic. So what we need to do is to look at the problems that the existence of mankind on this planet, the problems that we're creating, and to use some chemistry to try and solve those problems. And I'm going to give you a taste of the sort of the intellectual input of chemists in this lecture. So I thought I would go back in time. Sometimes we have a tendency as scientists to predict the future instead of going back in time and showing you where science had a major impact. So I thought I would go right back. In fact, the first written, or some of the knowledge about chemistry goes back centuries. It's no accident that mankind started off with the Stone Age And then we moved into Bronze and Iron Age, and now we're in the Titanium Age. So you don't mark mankind's development in order of when did they suddenly start to speak? We don't mark where they went from ugh to language. The way in which we mark history is, in fact, when we started to be able to use chemistry. That just shows you how fundamentally important chemistry is to your everyday lives. From the moment you brushed your teeth this morning. Now, my teeth, I hope, brush them this morning. But I just want to have a look, see if my teeth will glow for you. But if they don't, oops, well, they're already on low. They're not low enough. Hold on a moment. Let's try that's two front rows. I'm going to have to go for no, they haven't marked them all. I'm going to have to try. I'm ever so sorry, this is me applying the scientific method of trial and error. This is supposed to be all dim, but that doesn't look like all dim to me. So I think that's about as low as I'm going to get. Okay, so you might not see my teeth glow. Can you see my teeth glow? No. See from the look of you that you can't see my teeth glowing. But maybe you can see, this is tonic water. It's about now in the lecture that I usually feel I need some. And you see, you just about see it glow. You see the glow? That's a fluorescent material. It's the quinine in tonic water. That fluorescent material is put into soap powders, paint, me, and it makes things whiter than white, because in the UV light that shines on things makes things whiter than white. But anyway, I digress. Colours. Colours now, in Egyptian tombs, were made by taking some natural pigments and imported raw materials and cooking them up. The white came from magnesium carbonate, magnesium calcium carbonate. The orange is arsenic, is an arsenic sulfide, very poisonous. Hence the warning signs in Egyptian tombs. Enter here and you'll die. Well, if you lick the paint off the wall, you certainly would. And blue. Blue was the colour of kings. So you can see here's Ramesses with his blue hat, and that was made by embedding coppers into glass. Now, glass is basically sand, molten sand, but it melts at quite a high temperature. So to lower the melting point, Egyptians, back in 1170 BC, added salt. They were already applying some chemistry. And this is the first written account of a chemical procedure in which to make the blue colour of these royal objects. And it was a mixture of limestone, sand, and copper carbonates, which we call malachites. But if you go back to the 9th century, the Chinese had developed gunpowder, and they used the gunpowder in fireworks. And so I'm going to do a little bit here with some chemicals. They're quite interesting, because in fact, heating things, this is where I usually just turn it up a bit. Heating things is actually a very good way of finding out what's in them. So this is ethanol, same sort of thing, same idea as putting whiskey. You know when you burn whiskey on the Christmas pudding? But all I've added here is a little bit of potassium. And so what it will do is it will make the flame change colour. This is copper, and it has a different colour, has a green colour. And this one is lithium. And this is called a flame test, and you can actually use it. Gorgeous, isn't it? I have to do that one again. This is actually used to identify materials. Years ago, people used to burn things, and some of you at school will have done flame tests based on exactly this principle. What's happening? Well, the metals present in this ethanol, they have electrons. And electrons are light, tiny little particles that like to move from one atom to another. They're responsible for all the reactivity of an atom. And what happens here is because the electrons are kept in different places, when you provide them with heat, they move, and when they move, they give out a certain light. So it would be a little bit like me taking this lecture theatre and setting it on fire, and then going outside and see how long it took you to come out. I'd have an idea of where you were sitting, wouldn't I? Because if you were sitting near the front, near the exit, you'd have got out. But if you were somewhere near the back, you'd have burnt to a cinder. And so from that way, I can find out where you're sitting, where the electrons are in an atom, and then I can work back and say, you must be this atom here, because they're the guys that have electrons arranged in this way. Now, gunpowder was first written down, the recipe was written down in 1242 by Roger Bacon. He was an Englishman. No, you mustn't take that, hold it against him. Because so am I. Well, English woman. Now, so, always one to go back in time properly, I have made some gunpowder based on Roger Bacon's 1242 recipe. Now, gunpowder was notoriously temperamental. And what you'd do is you'd put a small bit of gunpowder into the bottom of your musket, then you would put a small pellet on top of it, and then the gunpowder would explode, push the pellet out, or the bullet, and shoot someone. The only problem is, quite often they had this tendency to backfire and blow up in the face of the person using the musket. So all I've got to do now is to find a volunteer. No, it's all right. I'm going to do it myself. But I always worry that I'm going to be like one of those cartoons, you know, when somebody goes to... But anyway, I should put my goggles on, got my white coat on, and if you're sitting in the front, it's because you were late, so I don't care. So, we'll see what happens. So, goggles on. I might just move the ethanol. Always wise to be sensible first. And then I'll have a glowing spint. Now, so this is the recipe as written there. If you want to have a look, you can see lots of people who have done this on YouTube to various effects. Oops. And hopefully mine won't be quite so catastrophic. Oh, I did mention fire exits, did I? I haven't got that lit very well at all. Doesn't want to light. Where's the good old-fashioned matches? Nope. I'm going to have to be very brave. No, I don't feel that that's sensible. Now, hold on a moment. I've got to think of this. I think this through. I'll try another one. I wouldn't come near me. And I will have one more go. Maybe I should make a try. That's a bit more promising. There we are. Oh, that's quite good, wasn't it? So, it still works. Now, if I compressed that powder, it would go with an almighty bang. And the reason is that in it, it's got some sodium nitrate or potassium nitrate. We ground everything up with carbon and sulfur, and the nitrates acts as a supply of oxygen, and they give their oxygen to the sulfur and carbon, making sulfur dioxide and carbon dioxide, which are gases. So if you contain it, the gases are desperate to get out, and there's a massive bang. But I didn't do that. I just kept it powdery and light so that it was all under control. Now here's another example where chemistry is literally a matter of life or death. And here you can see this is a gentleman from the Matis tribe in Brazil. And what he's done is he has worked out how to extract a poison called strychnine. And what he's going to do with that strychnine is he's going to put it on the end of his blow dart, and he's not going to suck, he's going to blow. And when he blows, he's going to force the dart out of this thin tube using a tooth of a large rodent as a sight, actually using a little focal point. And he will shoot a monkey down from the rainforest. Now, you might say, sure, so what? Well, what does that tell us? First of all, he knows which plant extracts the strychnine, knows the dosage for the monkey, and you mustn't poison the monkey too much because the meat will be poisoned. And he has to think about it, because if he gives the dart, if it's too small a dose, the monkey will run for 20 miles and he'll be exhausted by the time it falls out the tree. Or what he wants is a short response, 200 yards, drops from the tree, picks up the prey, food is safe to eat. Imagine what the effect of that must have been on mankind, that we could go from having to fire bows and arrows at something or stab them to death, to poisoning them to death. To just think that through. Here's another example of the use of strychnine in modern day. There was a gentleman called Thomas Wainwright. He was a serial killer in England. Problem was he had a very lavish lifestyle and he just couldn't afford it. So what happened was he started to persuade close relatives to take out insurance policies and then slowly kill them off one by one. The one that he eventually admitted to before he died, having been shipped off to Tasmania, was his wife's younger sister. And he used a mixture of antimony and strychnine. Now the problem with strychnine is that it has a really, really bitter taste. So you won't get somebody to eat enough of it to die unless you can disguise it. So he put it in jelly and fed it to her in order to make her feel better, as a cure for her tummy aches. And funnily enough, she died. So this is what the plant strychnine looks like. This is the house that he was trying to inherit, and this is the poor young lady who suffered the consequences of strychnine. So in other words, if you can extract strychnine, you can use it for good, for survival, and you can use it for bad. And that is always true with knowledge. You can use knowledge to better society, or you can use it for your own selfish gain. And that's something that is up to all of us to take responsibility. You can take responsibility for it is if you know it. So you have to understand it, and you have to either trust the people that know more or be prepared to teach yourself more. So this is something I would encourage you all to do. If you are naturally interested in science, you need to get yourself reading about it and finding out about it. You may never become a scientist, but it doesn't matter, because you'll be in a better position to judge the people who are making claims about their own findings. I'm going to take you now to a little experiment and show you something that happened several years ago. To this day, sulfuric acid is such an important chemical that you can almost measure the development of a society or the development of its industry from the amount of sulfuric acid the country is producing. And to make sulfuric acid, we use a catalyst. And the idea was first thought up in the it's about 1780 to 1850, around then, and it was a guy called John Jacob Berlioz, or Berzelius. Sorry, my Swedish, hence the terrible pronunciation. And what he said was that catalysis awakens affinities that are asleep. So what you need to do here is you need to make sulfur, oxygen, and water react together. And they react much more quickly and much more efficiently if you put them into a metal vessel. And these original metal vessels were made of platinum and copper, but they've now been replaced with vanadium oxide. And this is an example of heterogeneous catalysis, which means the reagents are liquids and gases, and the surface, the catalyst, is a solid. So they're different phases. So I'll just show you very briefly, before I do this, what the difference between a solid, a liquid, and a gas is. Okay, here is my favourite bit of the entire lecture. This is the arrangement of atoms in a solid. They are closely packed, and all they can really do is vibrate. This is going to be, hold on a moment. This is a liquid. Now, they have more room to move, and they can flow. Okay? And finally, this will take me a while to get to. This is a situation in a gas. Very few atoms flying around, occupying lots of space. And sometimes those little atoms can be so energetic that they can actually get through a wall. Say helium can get out of a helium balloon, and after a while it sinks. But anyway, here is my solid, and to represent the solid I have a Ferrero Rochers. Now I didn't eat this one, it fell out when the person was taking off the lid. So it's here somewhere. Anyway, I'm going to show you how catalysis works. Now what happens is, an atom reagent flying around manages to hit the catalytic surface. And when it does, it reacts. But the problem is that statistically, only 1 in 8 billion manages to sit on the surface and react in the right place. There's also another terrible inefficiency here, and that is that, of course, under the surface, there are lots and lots of atoms that are not being touched by the reagents, and so aren't getting involved. So what do we do? How do we make this process more efficient? In comes the chemist. Now, you may query whether I've got the mechanism right, whether the process I'm describing, I better put these down, or I ain't too many. Whether the process I'm describing is accurate. So, this is called a scanning tunneling microscopy, or microscope, and there's one atom on the end here, so this is an incredibly thin, tiny thin needle. And what we do is, in an institute attached to chemistry, is we have a few of these that are unique in the entire world. And what we do is we pass that tip over a surface, and it measures the current that jumps from the tip to the surface. And the current changes depending what's on the surface. So here's an oxygen attached to the surface, and over time you can see the oxygen atoms separate. When oxygen atoms separate, they become much more reactive. So this is evidence that this metallic surface is acting as a catalyst to break that oxygen-oxygen bond. But to make it more effective, what we could do is we could design the catalyst so it swims around as single atoms, and then it's free to bump into the reagents, which are blue, and turn into products, which are green. Super efficient process. Lots of catalyst atoms, all doing what the catalyst atoms are supposed to do, individually. Oh, won't it? But there's a problem. And I'll tell you what the downside is. The downside is, now you've got to separate the blue reagents from the green products. And the catalyst. It's going to be a mess. How are you going to slow this? This is going to slow the whole process down. So what would you do? Well, what chemists have done is they've created a Malteser-like framework. This is a honeycomb framework. They attach the catalyst to the framework, and then the reagents can flow through the membrane and do the reacting, turn into products, and out they come, separated. So you keep the efficiency, but you lose the problems of reactivity, of separation. So I just thought I'd briefly take you through a few of the things that we've managed to achieve using science, a mixture of biology, chemistry, and physics, but in all cases, chemistry is involved with making the active materials. And this is where technology has taken us. This tiny little chip is made up of lots and lots of layered materials, including materials that emit light, like the quinine, and have allowed us now to do the activities of an entire lab or an entire room full of computers on one chip. There is a problem, and this problem is not going to be solved without chemistry. And the problem is that we are using up our fossilized fuels, and we're losing up the raw materials on this planet at a rate of knots. And yet we have so many things we want to do with them. And if we run out, we'll be in trouble. There won't be plastics. There won't be nylon. There won't be raw materials to make drugs. There won't be, it's the oil that provides some of the raw materials that we need. So if we could reserve these precious materials for things that we actually need, and if we could find an alternative source of fuel, then I think mankind has a chance. And one possible answer is to be particularly mindful of reusing, recycling, and how you extract materials. So we need to really, really work hard on those things so that it buys us time. And with that time, we need to come up with an alternative energy source. And one of the possible energy sources is called a hydrogen economy, because when you burn hydrogen, it releases a huge amount of energy, and the only downside is the production of water. And you can reverse that reaction. You can take the water and turn it into hydrogen. And water, as we all know, is the giver of life. It's not the taker of life, like some of our carbonaceous poisons, if you like, the carbon dioxide poisons that we're putting in the world, the greenhouse gases. So lastly, I'll just show you some of the things that we're doing in chemistry. We always work on molecules, and a molecule is about an 80,000th of a diameter of a human hair. So it's absolutely tiny. So these atoms that I've shown you here are massively, massively multiplied. But let me just show you also how we can make materials that can interact specifically. This is DNA. This is the sides of the DNA, and these are what are called the step ladders that hold it together, the phosphate groups that hold it together. And if you think about it, in mankind, we only have right-handed DNA. So all our DNA twists this way, like a right hand. There is the very, very few creatures in the world whose DNA twists this way. So that we know that DNA twists that way, how can it be? How can statistically it be that we've created only right-handed DNA when two-handedness are possible? Now we have it. Can't we generate materials that will specifically only react between the base pairs? And if we do, when we make DNA in our bodies, we can stop the DNA from replicating. Why would we want to stop DNA from replicating? Because if there's a problem with this DNA, if it is cancerous, this is the DNA you do not want to photocopy wrongly throughout your body. So what chemists do is we create specifically designed little materials that interact with the DNA, preventing two sides from zipping up and from you and me having cancer. These are just some of the things that I wanted to tell you about today.